We're going to talk about polynomial characteristics in our graphs. So what are some key things that we are looking for each time when we are looking at our graphs? Well, we want to look at things such as domain, range, and behavior. So what's going on with our graph is it's going to the extreme right and extreme left of the x-axis, aka what's going on with those y values. Are they going to infinity or negative infinity? We want to look for our x-intercepts or zeros, aka where they touch that x-axis. We want to look for the y-intercept, where it touches our y-axis, if it has one, and then some turning points, also known as our relative maxes or mins as well, and if there are multiple of those. So we see here the graph given for this particular quintic polynomial, and we are going to use the graph that they gave us to guesstimate some of these points from the graph. So our domain and our range, if we look at this, well, our range is all real numbers. We notice that the graph this time is going negative infinity to positive infinity, going all the way. There's no max, there's no min. All y values will eventually be hit. Our domain for this polynomial and all polynomials is all real numbers, again, going from negative infinity to positive infinity x value wise. This time our y-intercept is at 0, 2. We see this point here. And our zeros, we actually only have one. It's where it's touching that x-axis. We have a 0 at just between 1 and 2, so maybe 1.5. Again, we're kind of guesstimating from graph. So we're using, again, the graph to approximate. So some of these are going to look a little bit more exact than other. Now, this time when we talk about our relative maxes, there are officially 1, 2 little maxes happening on this graph. This first one is at about negative 0.8, maybe 3.3-ish, a little bit over 3, not quite to 3.5. Our second little max is a little over 1. It's maybe like 1.1 for the x value, 1.1 for that y value. Our minimums this time, we have 2 little mins here, 2 little turning points. There we have one that is at about negative 1.1, just around 2.9, just almost below 3. And then this second point down here is a max at 0.7, 0.8, not quite to 1 for either of those. Now, as far as our end behavior goes, okay, as our x values, as we go this direction on our graph, what is happening with our y values? Well, as x's are approaching positive infinity, our y values this time are going really, really negative. They're going towards negative infinity. And as our x values are going towards negative infinity, this time our graph is going up. Right? Our y values are getting more and more positive, going towards positive infinity. On our next graph, this time we have a degree for a polynomial, and our range is going to actually depend a little bit on this minimum value down here. All of our y values are greater than or equal to this minimum value of maybe negative 4.2. Or we would say about negative 4.2 to infinity. If we're looking at interval notation bracket on that, we will include that negative y value. Domain, as always with these polynomials, is all real numbers, though. Our x values do not have any breaks. Our y-intercept this time is at 0, 4. And this time we have 2 zeros, one of them at 1. And again, a little bit of a guesstimate on this one, a little bit over 2. Looks like at about maybe 2.3 on that graph. All right, we have one relative max this time. It's actually coming at that y-intercept at 0, 4 would be our max. But we have 2 mins this time. The first one looks like it is at about negative 1.1, to maybe 2-ish on this one. Yeah, 2 would be our best on this one. And then our other minimum point, again, is kind of down here. Looks like it's at about 1.1, negative 4.2, 4 point on that one. All right, our end behavior. Again, each time as x goes to positive infinity, what's happening? And as x goes to negative infinity, again, you're always going to have those two things. Well, this time as our x values are getting bigger, so are our y values, right? They're also going to positive infinity. As our x values are getting more and more negative, the end behavior is also going up towards positive infinity. Now there is a graph on the next page then for you to try. You are stating each of these characteristics on your graph: the range, domain, y-intercept zeros, max and mins, and end behavior. All right, now some things we want to be able to analyze even if we're not given a graph. Well, one thing we can tell is our end behavior. And it's all going to be based on what degree do you have. If it's an even degree, they are either going to both ends be going up towards positive infinity or both ends be going down towards negative infinity. And what that's going to be reliant upon is your leading coefficient with that. Is it positive or is it negative? It will affect that graph. An odd degree with our end behavior, the leading coefficient is going to affect the x's as we go to positive infinity. Because if your leading coefficient is positive, this will be going towards positive infinity. However, if your leading coefficient is negative, as our x's are getting bigger, our y values will go to negative infinity and follow that trend. The other direction, though, our x's are always then going to be, our negative direction will always be opposite of whatever that positive direction was, because they are odd. We also could tell from just the function without a graph the max number of zeros. That's going to match the highest degree of our polynomial. Max number of turning points would be that degree minus 1. And then on the last page, we see this vocab word here, multiplicity. Multiplicity essentially is a zero that is of multiple degree in a graph. So for instance, if we look on this example graph here, we see at x equals -5, we have a multiple degree. Now, why would we know that even without looking at this function where we see it twice? It's because we see that bounce at our graph. At this time, it's a minimum value, but when you have an even degree there, like x minus 5 to the second power, you will see a bounce. When you have an odd degree, it's still going to pass through, but oftentimes what we're seeing then is a point of inflection. It'll pass through if it's just the first degree, but anything like 3, 5, 7, you'd see this point of inflection where it would peter out. And that's, we talked about in the last lesson, kind of some of those graphs that kind of flatten out in the middle like a cubic. That's your point of inflection. Last but not least, we are also going to be able to tell our y-intercept. We just would plug in 0 for x and simplify to get that output value, 0, comma, whatever that y-intercept is. So we see down below a couple examples. Again, we are going to not graph this to be able to tell each of these things. So first and foremost, what are our max zeros? Well, again, that's going to match the highest degree of our function. In this case, our highest degree is 5. And then the max turning points are going to be 1 less than that each time, and that's 4. Our y-intercept this time, if we plug in 0 for our x value, we would have 0 to the 5th power, and then minus 2 times 0 to the 3rd power, and we end up seeing our output value this time is 0. And then we want to tell our end behavior. So again, with end behavior, you will have as x goes to infinity and as it goes to negative infinity, what is happening? Well, we go back to, again, this beginning piece here because we see that this is degree 5, so it's odd, and the leading coefficient here is a positive 1. So we know that that means that this is going to go to positive infinity because the leading coefficient was a positive 1. Well, that because this is odd, Okay, when we have an odd degree, that means that this is going to be opposite of what the original was. It's going to go to negative infinity because it's opposite, because it's odd. So these will not match. On our next one, right, we have a degree 3 polynomial. So we have a max 0 number that will match that of 3, max number of turning points, that's one less than that, which would be 2. Our y-intercept this time, if we plug in 0 for x, we'd have negative 0 to the third, and then plus 3 times 0 squared minus 6 for an output value of negative 6. So you're going to notice when we're plugging in those zeros, they tend to cancel out. We're kind of just left with that remaining piece, in this case, negative 6. And then last but not least, again, we're looking at our end behavior. So then there's two pieces here. As x goes to positive infinity and as x goes to negative infinity, what's happening? Well, this time our leading coefficient is negative. So what that means is that our y values will go to negative infinity. And again, because the degree of our polynomial is odd, we know that our y values will go the opposite direction to positive infinity, the other direction. All right, our next example, we see degree 4 here. So max zeros will match that. We are going to also have 4. Max number of turning points, one less than that. So 3. This time when we plug in for our y-intercept, again, you're going to notice that this is going to simplify to 0, 0, 0, and we're just left with 1 as our y-intercept. And then we have to look at our two end behaviors each direction. As x goes to infinity and as x goes to negative infinity, what is happening? Well, this time we have a positive leading coefficient. So our y values will go to positive infinity. And this time, because we have this even degree, our y values are going to match, because if we have an even degree, these must match. Leading coefficient was positive, so they're both going to positive infinity. All right, last example together then here. Notice on this one, it's a little bit interesting because we actually don't have the polynomial worked all the way out. But if we did expand this out, we have a degree 1 here, a degree 2 here, a degree 1 here, for an overall degree of 5 on this polynomial. And then we, again, can look at max zeros. From that, it's going to match that degree of 5. Max turning points then, 1 less than that, it will be 4. Y-intercept this time requires slightly more work because everything may or may not cancel out. So just to double check, we're going to plug in our negative 2, x is 0 minus 9, and then we have 0 plus 2 quantity squared, and then 0 plus 1. We see our output for our y-intercept this time is actually positive 72. So way up on that graph. All right, end behavior this time. Okay, we have to go off of two things. Again, that leading coefficient and then the overall degree. So this time our leading coefficient is negative 2, which means our y values are going to go to negative infinity because that leading coefficient is negative. And then we also are going to notice on this one that since this is a degree 5 and is odd, our graph is going to go the opposite direction as x's go to negative infinity. There is one last example for you to try with the max zeros, turning points, y-intercept, and then your end behavior. Thanks everyone for watching. We'll work more with activity 9 in class.